Okay, let's look at the different types of titrations and the calculations that you will do. So a strong acid, strong base titration. This means that we have a strong acid and are titrating it with a strong base, or we have a strong base and are titrating it with a strong acid. So I'm going to show you the titration curves and point out the different features about these curves. So on the left, I have a titration curve in orange where the pH starts around 12 and it ends around 1. So on this pH curve, the analyte is the base. So the strong base is in the Erlenmeyer, it's in the analyte flask. And the way that I know this is because the pH that is measured is the pH in the analyte flask. So I'm starting out at an extremely basic pH. So my titrant is the strong acid. On the right, in blue, I'm starting at a pH of 1, ending at 12. My analyte is the strong acid. My titrant is the strong base. This is, in general, what all titration curves are going to look like, but specifically for strong acid and strong base, they are going to be very flat and very nearly vertical and very regular looking in terms of the curve part. I've also marked the equivalence point, which is always about, it's like halfway up the vertical section of the titration curve. Officially, equivalence point definition, this is the point at which all analyte has been reacted. And for a strong acid, strong base titration, or strong base, strong acid, whichever order you need to put them in, the pH at equivalence will be 7 always. Or if you get a pH at equivalence, then you know for sure that you had a strong acid and a strong base. The reason the pH at equivalence is 7 is that if you react perfect amounts of the acid and the base, the products of that reaction are water and then a salt, and the salt is made from the conjugate acid of a strong base, so it's neutral, and the conjugate base of a strong acid, so it is also neutral. For a weak acid and a strong base, or a weak base and a strong acid, the titration curves look similar, but they're not quite the same. So on the left, I have in orange, I'm starting at a pH around 2 and ending at a pH around 12. So this is starting with an acidic pH. So my analyte is an acid in the curve on the left. I'm adding base, so my pH is going up. And then on the right, I am starting with base. So my pH is around 10. So this is my weak base titrated with a strong acid. Looking at these, one of the ways that they look different from the strong acid, strong base titration curves is that the initial section, it's kind of flat, but you can see it's got a different shape. The pH might go up or down a little bit initially, but then it really stays the same over an extended period. And that's because when we have a weak acid or a weak base in the analyte flask, and you react it with a strong acid or a strong base, the product that is made is the conjugate of the thing we started with. So we have a buffer solution in our analyte flask for these titrations. I've also marked the equivalence point on here. The equivalence point in my weak acid, strong base titration, it's at a basic pH. And the equivalence point in my weak base strong acid titration is at an acidic pH. This is because when I'm at the equivalence point, I've completely reacted my weak acid, and everything left in solution is the conjugate base. Then the opposite for my weak base, I've reacted all of the weak base. Everything left in solution is the conjugate acid. So when you are looking at these titrations, and especially when you're doing any type of calculation at all, the question that you should ask yourself is what is in the flask? What did I start with? What have I added? Did they react with each other? What am I left with? And then with what I have left, how do I calculate the pH? So I have some equations here to go with the buffer claims that I made off of my weak strong titration. So if you start with a weak acid like acetic acid and react it with a strong base, so I could just say OH minus, because if it's a strong base, it's fully dissociated. My product is acetate and water. So the acetic acid acetate combination makes that a buffer solution. If I were titrating ammonia with a strong acid, which I can just write H plus because if it's a strong acid, it's completely dissociated, then ammonium would be my product, which is the conjugate acid of ammonia. When you get to the equivalence point, only the conjugate remains. So I have my same equations here. The acetic acid is completely gone at equivalence. So the only thing present that is affecting the pH of the solution is the acetate, which would make it basic. And then if it were the other titration, it would just be ammonium. So for titration calculations, always ask yourself what is in the flask. Once you've determined what's in there, you want to react those things with each other if they react. And you will use the reaction stoichiometry to get moles. So you'll probably take concentration, turn it into moles, figure out how many moles are left, and then turn it back into a concentration. So first of all, for that, keep track of the volume. Once you have the things that are left over, it will fall into one of the categories that you already know how to do calculations for. So you might be left with a strong acid or strong base in solution, and you know how to calculate the pH of that. You might be left with a weak acid or a weak base in solution. You know how to calculate the pH of those. You might be left with a buffer solution, which you just learned how to calculate the pH of, and you might be left with a salt solution, which you do also know how to calculate the pH of. So what is in the flask? Do they react with each other? What do I have left over? Out of the things I have left over, what affects the pH? And then how do I calculate the pH of the thing left over?